Hello and welcome. I hope everybody can hear me loud and clearly. Um, Welcome to this webinar from Force Technology titled Practical Use for Hybrid Testing and Simulation. We have allocated 45 minutes for this webinar. We expect the presentation to be about 35 minutes, after which we'll be more than happy to answer any questions. If you have any questions, please use the Q&A button in Teams and type in your question there, and then we'll take them at the end. And I think let's begin. To be on time on a Friday. Let's see here. Yes. Today we have 4 things we want to tell you about. First, we'll do a small introduction to ourselves, to Force Technology, and to today's subject of hybrid simulation. Then we talk about why we have chosen to focus on hybrid simulation. What is the aim of Force Technology using this? And then we have 2 examples we would like to show you and share the results from that we have done with 2 examples we've done within the last year. And then we would like to tell a little about the future work that we're planning and hopefully maybe entice some of you to join us in that work. But to start off, maybe I'll just tell the slide here. Yes. My name is Per Jensen. I'm a test engineer at Force Technology for 8 years and been working with large-scale climatic and mechanical testing. And with me today, I have Anders.
Yeah, and I primarily work as a project manager in our development work, primarily focusing on digital twins and hybrid simulation. And I have a background in fluid mechanics, numerical simulation, and experimentation.
You talked about background. My background is in nanotechnology, so it's not related to this. This is not. There it is. So Force Technology is a part of the Danish Research and Technology organizations. I think there's about 8 institutes in that organization. Force covers a wide range of fields, and that results in us having a lot of unique facilities, some of which we'll be talking about today, but also contributing to different types of collaboration projects with the industry, with universities, or R&D projects. Some of these projects we'll be talking about today. But we'll start talking about some of the facilities. My department, Materials and Components Test, is partly located at the old Maersk shipyard Lindø on Funen in Denmark, where we have 2 large facilities for one for climatic testing, large-scale climatic testing, and one for large-scale mechanical testing. So the climatic chamber we can control 3 parameters. We can control the humidity, we can control the temperature, and then we can also add salt spray for simulating offshore environments. We have also added the different extra units for simulating sun in there. We can do exhaust extraction. And then we have our large-scale mechanical bench. That's the right image in the top here, where we can do different types of large-scale mechanical testing. We do fatigue testing of welds. We can do design verification tests, many different things. We can have up to 6 actuators running at the same time, hydraulic actuators. And the industries that we cover in these 2 facilities are primarily wind, infrastructure, transportation, and defense. More and more defense these past few years. So that's my department.
Yes. So Per is representing the physical part of the presentation today, and I'm representing the virtual part of the competences today. And I come from the department where we do advanced flow simulation, and we can basically apply our simulations in most fields that have anything to do with flow management, distribution, and so on. But primarily we work in the areas of ventilation, clean air services, life science, power to X, maritime, carbon capture, and so on. Where we do consultancy work for our clients in terms of designing new components or optimizing existing production, or what's it called, error detection. If there is something not working the way it's supposed to do, we can go in and investigate why that is, and then come with recommendations to how to fix that. And as a few examples, we do optimization of waste to energy combustion chambers. We do designing of airflow in a clean room for life science, and baseline optimization of operation of medical devices, emission reduction. And as the image here shows, we can also help in assessing safety around leakage with emerging power to X industries. There can be some concern about leakage. What happens if ammonia, methane, hydrogen, and so on, if that leaks from a tank or production facility and so on, and we can then assist in saying, due to weather and so on, how would that affect the surrounding area. Yeah, and then we use these in different types of projects, and one of the two of the projects that found the foundation for what we're talking about today is that from the wind energy, Per's department has working on some of the physical testing, and we have worked on some virtual models from the hybrid testing approach, and we have come together in this project called DLT, Demonstrating of Lifetime Extension. And that's an EUDP project. And if you want to know more about these in depth, there's these QR codes on the slides where you can will be sent to the webpage of each of these projects, and they will be throughout the presentation as well to give you guys more information about some of the topics that we are talking about today.
Mm-hmm. Should we just add, because I know the people like that, the two projects on the left, they're funded by the Danish Agency for Higher Education and Science. And the one on the right, DLTE, which we'll get back to, is funded by EUDP, which is not an EU program, but a energy ministry program, I think, for Denmark. Yeah. So, yeah, it took me a while to figure that out when I first started. And so that was the introduction of us and FORCE, and so now we will, and the projects we were working on, now we'll switch to today's subject, hybrid simulation. Hybrid simulation has been around in research and university environment for, I think, 50 years or something like that. That also means that the terminology is a little bit, I don't know if you should set in stone, but it also differs maybe from field of usage. But in order for us to make this a little bit more approachable, we just try and define it very simply as we have a virtual model on our left here in as a jagged structure, which we'll get back to in one of our examples. We have an experimental setup with an image taken from our large-scale mechanical testing facility. And then the combination of those two, the interaction between those two, that is our hybrid simulation. Can be a very powerful technique if you set it up correctly, that can advance both the model and the testing, the quality of those two components. when we talk about where to use hybrid simulation, you often talk about you want something non-linear for it to there needs to be a non-linear element in your project, whether it be non-linear physics or behavior or response from a system that helps you increase the quality of the system. Yes. So that's overall hybrid simulation. Very, very, very quickly.
Broad strokes.
Broad strokes. Again, we want to focus on the practicality of how we actually use it at FORCE. There's a lot of literature that you can find online that talks about what it is and how to set it up. For our aim at FORCE Technology, we focus on hybrid simulation for generating data for improving decision making and optimize the performance and durability of complex systems. Very, very fine line, but that is the focus. Either we optimize the data generated by the model or by the test. But we try and divide hybrid simulation into three different topics, let's say. So we define it as hybrid sensing, hybrid testing, and hybrid simulation. So in hybrid sensing, it's a one-way traffic from the test to the virtual model. So here we can use real-world data from the test, from in-service usage to calibrate a model, and to then in the model have, for example, numerous sensors that is then calibrated on maybe just a few real-world sensors. So you can, in a very easy way, have a lot of sensors instead of having to apply 1,000 strain gauges or 1,000 temperature sensors. On the other hand, we can do one-way traffic the other way, from the model to the test. If we, for example, want more real boundary conditions for a test, then we can use real life data, and then from the model dictates how does the test correspond, how does it execute the test. The model in this case does not care how the test actually responds to those boundary conditions. It just said this is how it is. Then in the final version here, hybrid simulation, we have two-way traffic back and forth between the model and the physical test. So the model comes with its boundary conditions to the test, and then the test sends back data. The model updates itself and sends new boundary conditions if needed. And it's the last thing here that we will share two examples we have done the last year. And we'll start with Anders presenting one example.
Yes. Yeah, so the first example is the before mentioned UDP project, which was a cooperation between us at FORCE Technology and R&D Test Systems and Aarhus University, where the goal was to assess lifetime of wind turbine components. So the purpose is, how can we utilize hybrid simulation as a tool to gain this insight into the lifetime of our used wind turbine components? And that means there's different ways of doing this, and a very classical way would be that you find a used wind turbine and you put a lot of sensors on this, and then you wait for certain conditions in the weather so that you get the data that you need in order to verify the end of life of these components, whether they are close to that or, well, let's say there's 20 years left on this wind turbine, in something that changes over time due to the effects of each area where these wind turbines are placed around the world. Another way is that we say that we have some key components of this wind turbine, and say we have a hard time modeling these, or we want some specific information from these. So we focus the physical part of our lifetime assessment. We focus on these components, and then we model the rest of the wind turbine. So in this case, we have a little experience here from Per's department in doing testing of pitch bearings. Pitch bearing is the ball bearing that is situated in the wind turbine between the hub and the blade. So the joint that enables the blade to pitch in the wind due to different wind speeds and so on. And this bearing is affected in a little weird way during its lifetime. So it's a nonlinear behavior component, and also in a nonlinear behavior system. So what we did is that the result of this project is that we have a virtual model that models the aerodynamic forces. So from the examples or the different types that Per described earlier. So in the hybrid testing, for instance, where we model the input for the physical test, but we also model the entire wind turbine based on the sensors from the test. Meaning that this is a two-way coupled system. Yes, so we have the model on the left. There's a simple model of an entire wind turbine taking in wind data, modeling the aerodynamic, rotational, gravitational forces, but it also models the response of the tower, so that the forces that we actually apply to the pitch bearing in the physical experimental setup is both based on real-world data, but it also calibrated to the reactions of what is actually happening in a wind turbine when you put all of these components together, instead of just testing the bearing by itself. Yeah. Other than that, for this to work, you of course need a data management system in the background, which is capable of sending this information back and forth between these two setups. And in doing so, we actually managed to do a system where a little side note, is able to separate our IP as well. Because in this instance, we at Force Technology was responsible for the experimental setup and part of the data management, but we were not responsible for the virtual model, and we were actually able to run the virtual model externally outside both our network and outside our control, and that meant we could send the data back and forth that was only connected to the sensors and the forces we needed for the data setup itself. Yes. And of course, yeah, we get some challenges in computational time and so on, because due to all this communication back and forth and the calibration of the setup, we have here a small sequence from one of the many tests that we did. This is a sped up video of approximately half an hour of interaction between our stakeholders and viewing this test setup. But the actual simulated physical time that we were able to do in this half an hour was actually only 4 seconds. And that is because we ran the test at 100 Hertz, and each time step that we apply and calibrate the forces input, this round trip takes 4 seconds. So each time step takes 4 seconds, and if you then have 100 time steps per physical second, then we suddenly surmount to half an hour. Yeah, but that basically looks like this, and just to let you know a little bit about some of the numbers running out here. So the two graphs on the left where you have some dashed lines and some full lines, that is the model predicting a force and then calibrating the force as well. That's why there's two sets of data on top of each other.
Mm-hmm. Maybe just to add, then you can see that the physical one has some noise around 0 due to some slacking in the system. So you can see that that's the physical part that plays in there. And if we just play it again, then if you're not sure that it's actually moving. Sorry, we just jumped ahead. It's actually moving. If you look at the bottom blue actuator, you can see it actually extending a little bit. So we are actually moving a little bit, but not a lot. Should we just say a little bit about that we do this simulated response that we test physically and in a collaboration between the model and the physical substructure. So that's 4 seconds of wind turbine action.
Yes.
Then what was the idea then? What are we going to do with those 4 seconds? And sorry, but then we were going to try and wear out the bearing to see, okay, does then the response change? And then we could foresee a testing regime where you did a hybrid simulation, you did some wear on the system, you did a hybrid simulation again, and so forth until you saw the response change, and then the model had to recalibrate itself to that and see how does the behavior change over time. So this wasn't a system where you expect that the physical test and the model were connected 24/7. This could be a check on a test from time during a lifetime testing, for example, to see that the model is calibrated to how it's behaving. Yes, very fun project, I would say.
Indeed.
Which brings us to our next example. We the project I mentioned here allowed us to build up the needed infrastructure to do hybrid simulation. But we wanted to do hybrid simulation where we didn't do 4 seconds of hybrid simulation and then doing half an hour, and then maybe again in 4 weeks we did 4 seconds. We wanted to do something where the model and the physical substructure were connected for a longer period of time. So inspired by colleagues at DTU, we did what they have coined fatigue hybrid simulation, which we'll get more into detail, of a node from a jacket structure. And this project would then, we had some help from Travis, who specializes in repairing of offshore turbine components. We'll get back to why they were involved. But if we show you this slide here again with the virtual model of a jacket structure, the experimental setup here, we'll call this a T node due to the vague resemblance to a T, I would say. But it's a 90 degrees joint between 2 pipes. And then we have this overlay of the two on the right side, in that we have the location of the T node down at the bottom of the jacket. And then we combine it. And then hopefully we obtained more, the purpose was to obtain more realistic data from the fatigue test of such a T node based on constantly updating the boundary condition of the fatigue test. So that is what we're trying to obtain here. We'll just quickly take a look at the 2 elements in the hybrid simulation here. There's the T node, and it's set up in a experimental setup that we've also been using for classic fatigue testing. But just to reiterate, the method we're using here is that we will update the boundary condition of that fatigue test based on the model. So what we're aiming for in the test is to induce a crack in the hotspot zone indicated here on the T-node. The T-node is two pipes welded together 90 degrees. And you can find these these joints in offshore jagged structures. There are other joint geometries, but this was originally tested in a innovation fund project called CJagged, where the purpose was to investigate fatigue lifetime and how that could be extended by doing post-weld treatments. And if you want to learn more about that project, you can look into the QR code. There's also published articles about the results from that. But we asked permission, see if we could reuse one of the T-nodes, and we were given permission. So we had Trevis repair the T-node. So because then we could see, okay, in the beginning, we can say original T-node versus repaired T-node. And then once we start to get some changes in the boundary condition, then it becomes a hybrid simulation. And then the repaired part shouldn't matter as much. The other part of the hybrid simulation is our virtual model. In this case, it's a simple FE model of a somewhat simple jagged structure. I'm not going to say that this is how they build them offshore, but we asked some in-house structural guys to make us a simple jagged structure, and this is what we got. And our T-node is then located at the very bottom, where we have one of these 90 degrees joint connections. And then the force that we are applying, the force that this T-node is experiencing in the model, is then based on a single force applied at the top, and then it's modeled how that is redistributed within the structure. Then the compliance of the joint comes into play. We expect that the compliance of the joint will go down as we start to see a crack. And then the model will then tell us how the forces internally are redistributed once this compliance goes down. And then we'll send out a new boundary condition saying, now we're not experiencing the same force at that joint. So this is the boundary condition for that particular joint. That is the overall idea. But so so that we have something to compare it with, just to be very clear what we're trying to do. When we originally tested this specific T-node, we inserted a force, a sinusoidal force, with a constant amplitude in the sinusoidal force. So in principle, we weren't changing the boundary condition, they're constant. We switched the test ran in tension, so from a minimum force above zero to a maximum force somewhere above zero. We were pushing upwards with this black actuator. From the test, we were monitoring strain, measured from strain gauges located close to the hotspot that we're trying to induce the crack, and then displacement from the cylinder as it moved up and down. And in the two graphs here, we have in the top, we have some strain that we can see once it starts to drop, that corresponds to when we have the crack initiated. And once it starts to go to zero here towards the end, that is when our crack is through thickness. Then the classical fatigue test is done, and we have our result. It took this many cycles for the sinusoidal force to achieve through thickness crack. Through that, the other data we can look at is then how much do the actuator move to apply the force, and that also starts to increase once we have a crack. So the joint stiffness goes down, allowing needing for the actuator to move even more to put the same force on. This is what we'll utilize in that the stiffness goes down. We send that to the model, get new boundary conditions. So just to make it very clear, the model sends out boundary conditions for the force. We apply the force. We get a stiffness back based on the force that we're applying and the displacement that we're measuring. We convert that to joint stiffness. That joint stiffness set into the model. And then the model say, okay, this is your boundary condition based on the joint stiffness you just gave me. And then we set it up so you don't have to change for every single cycle, because the testing program was not set up for that. We set up if we constantly monitored the boundary condition for the force that the model gave us, and said if it differed by more than 0.05%, then we need to stop the test, restart it with the new boundary conditions, and then so forth. So it's an iterative process where we constantly monitor the input from the model, but only stop if there's a significant change to the boundary condition. And that gave us some results. We started with a maximum force that we applied of around 105.5 kilonewtons. As the joint stiffness changed, there was a crack initiation. Then we started to change the force boundary condition, and that happened 97 times from the first one to we say, okay, now we have to stop the test. The test is constantly stopping in order to have new boundary conditions. So the joint stiffness is changing rapidly at this point. And the final set point for the force was then 99.9. Now, unfortunately, the test didn't behave exactly as we expected. We expected to have a crack at the bottom here, but around 125,000 cycles, we detected a crack at the top of the joint. And then we continued to run until we had a crack at the bottom. And then once the bottom crack was there, we already the joint stiffness was changing real fast, and then we stopped the test. So this was a test where we tried to get to a non-linear state, where we have a steel structure here that behaves in a way that's hard to model. Whether or not it was the best candidate for such a test, that could be discussed, and I think we just got a question we'll talk about afterwards. But that was our two examples. So we'll talk a little bit about how we see us working with hybrid simulation in the future.
Yes, so based on these two examples, we would like to further explore the usability of this new hybrid test framework. And how we want to do that is that we would like to have new projects with new physics involved in it, and preferably also new test facilities. So as the facilities that Per mentioned in the beginning, we would like to develop our hybrid testing, hybrid simulation in our climatic chamber as well. And this will allow us to test the generalization of this framework, so that we will be better in the future at applying it both internally at our test facility, but also helping you guys setting up hybrid testing externally, so at your facilities, for instance, and then further exploring these different ways of doing hybrid simulation, as we talked about earlier, the hybrid sensing, hybrid testing, and hybrid simulation. So yeah, that's what we're focusing on. And currently we have two projects like before as well, which will allow us to get started in the climatic chamber and testing all of this. So for the immediate future for hybrid testing here at Force Technology will be focused in the area of wind energy and the defense and space, where we will utilize the hybrid testing in the climatic chamber with different outcomes, hopefully. But we're always looking for new possibilities for collaboration. So If any of you have some ideas based on what we have been talking about today, then please reach out for us.
Our contact should be somewhere in all the information that was given about this webinar. Yes, we reached the 35-minute mark, so just as somewhat promised. Just want to quickly, vaguely summarize what we believe that we have performed. We have hopefully shown you that hybrid simulation can be a useful tool for improving models and testing. We have shown you that we have it, so it's commercially available. And in this DLTE project, we have been able to do it without compromising IPs or setting up, let's say, a system that can secure IP. Now is the time for any questions. We have received some, but if you have any question here in the last part, feel free to put them in the Q&A. One final remark is that this is being recorded and will be on Force Technologies YouTube channel at some point. So if you didn't get the QR code for something, or you just want to revisit something, check out that. We will not distribute the PowerPoint itself or the slides. So there will be an email with that link at some point after the show. But on to the questions. We have a question here. In what case is it relevant to initiate a crack and then to continue to run? Is it if something has already gone wrong? So we can completely agree that we ran the test for much longer than you would normally do in fatigue testing, in terms of this T-node testing. We ran it way beyond proof thickness crack, so way beyond the lifetime. But for us, it was interesting. We wanted to get to a point in the test where the hybrid simulation was working, where the model was changing the test as it went along. Was this the best candidate for hybrid simulation? Maybe not, because it's a very stiff structure. It's a weld between two pipes is a very well-known structure within that field. So there's maybe not a lot of new information to gain there. But we are looking into other systems where it's not as well known. And then we have let's say, a well-calibrated sample to then see, okay, this is how we expect it to behave.
But the goal here as well was also to see, can we start a discussion about, is there a different behavior of our system if we apply forces to our system that is more realistic and closer to the real world condition? And I would conclude that we can clearly see that the behavior of how the test is performed is different from the original test, meaning that there is something here where our classical fatigue testing differs from a test in hybrid simulation, where we try to come closer to the real world conditions of, in this case, a T-node section.
But we had some interesting conversations with designers of jagged structures in it, and we said, we never get to that point. You know, there's too many safety factors to get to the point where you have a full thickness crack, and then everything's gone wrong. But it is interesting to see that the model changes the test. But then what could be really interesting, because we also know that the jagged redistribute the forces. So the force is low at this one joint, but then at another joint, it increases. So you could then have 2 or 3 tests running simultaneously. Okay, as it goes down on this one, it goes up on this one. How does that affect the lifetime of that joint? So hybrid simulation also allows us to then say, okay, we can have multiple tests running that can influence each other via this model.
Exactly.
Yeah, and then I think, you know, you don't start to run, you need to crawl and walk. And for our case here, we needed to crawl with a T-node test. And then it was also to see, can we have this test run automatically? Can it go to the cloud, constantly get new data, stop the test, restart it, completely automatically, and that we achieved in this. So that was very nice to see that we were able to do that.
Exactly.
For that test, we had our model internally in a cloud there, but it could have been externally.
As well as the other projects.
And then you would then yeah.
We have another question about what would the hardest be, what we found the hardest to be in setting up this system. I don't know if you want to take that on or.
I guess I have to answer because it's definitely on my part that just allowing access to the data management system of the physical test, getting data out from that and into that, and then figuring out how to update the system, that was definitely the hardest. But I also know that some of our IT guys had some issues as well.
Yeah,
so
I think
communication.
I would add to that and say one word in itself was the hardest. That was interfacing, and what I mean by that is both in terms of software, hardware, but also people, because there's so many different specialities and competences going into working with this. As you said, IT, physical testing, virtual model, reduced automatic, everything, and getting all of this working together, both in terms of culture, but also in terms of IT and hardware. That has definitely been the hardest to implement.
But also the most rewarding, being able to work across.
Definitely.
I would say when we work with Aarhus University and they had something where they need to change displacement to force and use some kind of very advanced mathematics, we were some who were, needed to listen very careful in order to follow. We have another question here. Whether or not we use commercial tools for data acquisition and FE simulation, or is it all based on in-house tools developed by yourself? I think everything we have in that regard is, well, mostly everything is commercial tools. We use an MTS system for our hydraulic testing. I think, is it ANSYS for the FE model?
Yes.
But in the communication between some of these parts, I think we have had some in-house IT guys develop.
That's primarily in-house development, because there's so many different programs out there to try an interface between programs, and then you have a program for the interface and a program for management. It gets very messy very quickly.
Yes.
So that's primarily in-house development for the data management system. But everything else, as Per said, the data acquisition, the simulations, and so on, that's based on commercial software.
Yes. There's very, very specific here if you use expanding pin in the hydraulic cylinder to remove backlash where the hydraulic cylinder was connected to the test rig. No, we did not. I think that's the quick answer. But I also see that there are some very specific questions, and I then urge to then contact me with an email or maybe set up a Teams meeting if you find this very interesting or have some specific ideas you want to test. I think we should stop a minute early. It is Friday, and we want to get a head start maybe on the traffic. Thank you very, very much for joining us on our little webinar here today. It was a pleasure, and with that, I think we should just say goodbye.
Have a nice weekend.
Have a nice weekend. Bye.